Okay, thank you very much for the introduction. So, in this lecture, I would like to give an overall overview of the field of network theory and tell you why in this field there is increasing interest in topological methods and study of simplicial complexes. So, network theory is one of the most prosperous fields of the last 20 years with a community which is interdisciplinary and very, very extensive. So, giving an introduction to this field is quite a challenge. I structured my lecture with this outline, but I would like to keep this very interactive. So, if we we will not be able to stick to the program, that's fine too. So at the beginning I will give an introduction, and I will tell you about one of the properties that people have been discussing in the context of networks quite extensively, which is a large heterogeneity in the degree distribution, and these networks are typically called scale-free. And I will try to motivate why people have been interested and exciting about these results that many real networks are scale-free and what are the implications. And then I will focus on one or possibly two methods for modeling complex networks. And I will show you that actually, since people are starting to think that in order to analyze big data is very important to use simplicial complexes and topological analysis, the field is moving in this direction, and these methods to model complex networks have been recently extended also to simplicial complexes. So, what are networks? Well, networks are graphs. Mathematically, we will say that are graphs, but we call them network because we want to stress the fact that these are graphs that indicate some real system, a real large interacting system. And these range from social networks to communication networks to biological networks. For instance, this is a collaboration network of scientists. The other one is a social network of people in a health study in which they study the kind of spreading of behavior. In this case was kind of obesity. Or you have the internet. The internet is one of the first maps that has been studied with the network approach, and is quite a beautiful example of man-made but a self-organized object. So it was a kind of a surprise at the, about 20 years ago, but actually it's also quite interesting to study the similarity between some man-made network and some biological network, like the protein interaction map, or the network between diseases that are caused by the same mutation of the same gene. So although these networks are very different, there are general questions that can be asked. And these are how do they respond to perturbation, what is their structure, what is their topology, and so on. And this has been attracting the field for a large time now. So if we really consider all the space of possible graph, let's say all the space of possible graph with the n nodes and n links, we have a quite big space, and at one end we have completely random graph in which a set of nodes are connected completely randomly with a given probability. At the other opposite end, we have a very regular structure like lattices that have been studied a lot in crystallography study, in physics. And in the middle, we have these objects that describe real systems that are intrinsically stochastic, in which there is a lot of randomness, but at the same time, they are not completely random, and the idea is that by studying the structure, we can get some insight about their function. And despite these networks are living in this very wide space in between these two extremes, they have been shown to display several universal properties. And these are been called the small world distance property, which refers to the fact that actually many networks have a small diameter. In some sense, one can say that they have an infinite Hausdorff dimension, and they have community, and so the region of the network which are more densely connected than other region, and they have also this scale-free distribution that I will on which I will focus mostly because we have a limited time. So people have been attracted by this research because the idea is that really the network encode information. So by studying the structure, you can get information, and in particular, I think you have learned from the blue gene simulation that this is actually important also to understand the brain function. And so what is a graph? So I just list there my terminology because it's not the usual mathematics terminology. So I will refer to vertices as nodes, and we will call them n nodes, a number of links, capital L. And a network, we will consider simple networks, so undirected and unweighted, which are typically specified by an adjacency matrix, which is an n by n matrix of one of elements which are one if node I is connected to node j and zero otherwise. And what do we mean by degree? Degree is just the sum of the links of each node, and the degree distribution is the fraction of node of a given degree. So in the 1960, there was a very important idea and in graph theory, and this idea was to include probability in the study of networks, and this was the work of Erdős and Renyi, which introduced random graphs. So random graphs are formed by a set of nodes and a set of links, or just by a set of nodes in which every pair of links is connected with probability p. And here the degree distribution is binomial, but actually if we are interested in the limit in which the number of links scales like the number of nodes, like we have in lattices, for instance, this degree distribution is Poissonian. So this is a very degree distribution with a precise mean and finite fluctuation around it. So if you imagine a social network to be a Poisson network with every people with 100 friends, the standard deviation is around 10. And so you will never expect to see someone with more than 10,000 links or things like that. While in Facebook, this is like every day. I mean, the big stars have these numbers and even higher number of links. So this brings us to the story of heterogeneity in nature and in society, and this story is a bit dramatic because it is a story of disparity, but Pareto was the first to observe that 20% of the people receive 80% of the income, and actually, this is still becoming more and more extreme. And you have this heterogeneity also in the frequency of word in a text or in the size of the cities and things like this. So we have that also in networks. So we can expect to have a power law networks with different exponents. And so for For gamma greater than 3, we have, so we are, here the figure is to show you that we are interested just in the asymptotic, in the behavior for large k, not in the beginning. And for gamma, for the power law gamma greater than 3, we have average degree, which is finite, and second moment, which is finite. In the region gamma between 1 and 2, both the average degree and the second moment are diverging with the network size as the network increase. And for gamma between 2 and 3, the average degree is finite, but the second moment is diverging. And actually, these are called the scale-free graph. And this indicates that if you have a social network and you sample and then you double your number of nodes, then the average degree remains practically the same, but the fluctuation, this average degree, is not really significant because the fluctuation around the mean are diverging. So the error that you make on the average is infinite. And these are many different type of network, and the difference can be schematically represented as the difference between a road network in which every city has more or less the same number of road passing through it, and the airport network in which you have big hubs. And so these hubs are the one that make the second moment diverging. And these networks, of course, there is a lot of debate if real networks are really power law or not really power law, but generally speaking, the fact that the second moment of the degree distribution is rather large and seems to diverge in the network limit is a property shared by many different systems that have very different nature. And starting from biological networks, going to the internet, which was one of the first networks that was studied, and social network, online social network, and so on. So here we are quite familiar with this universal property, but actually still, if you think about it, it's still a puzzle, while systems that are so different might share something in common. And so one answer is that is one of the most popular answers, is that actually the dynamics which generate this graph is kind of universal. But there is also another answer which I find really more satisfying, probably, which is the fact that these systems are very robust. So this system responds well to perturbation. So if there are mutation and perturbation, damage of some nodes, they still are functional. And by one proxy of functionality of the network is the measure of the giant component. So the component, the largest connected component that is of order of the number of nodes in the graph. And so people, when studied the robustness of the network, takes a network and damage the node with the probability 1 minus p. So p is the probability of non-damaging a node, and then looks at the giant component, how is reduced after the damage. So the fraction of nodes in the giant component is what is called the order parameter of this system. And so for Poisson networks, you have that as you start to damage, so you go from high p to low p, the fraction of node in the giant component decreases continuously. And at a certain moment, at k average equal 1 over c, the network is completely disrupted and dismantled. So for scale-free graph, actually this threshold goes to 0, meaning that you can keep going and damaging, and since these hubs, they keep the network together, you can damage practically almost all the graph node of the network, and you still have a giant component. So, and this can be theoretically predicted, and the percolation threshold, in fact, depends on this ratio. And here you see popping up the second moment of the degree distribution. This is diverging for scale-free graph, and so this is a percolation threshold that goes to 0 in the thermodynamic limit for infinite net.
That's a view that supposes the word is friendly, because in fact, this is because the DET here, the calculation is random.
Yes.
If on the contrary, the word is adversarial, it's much easier to construct a scale-free network than
yes.
just kill. That's what the wall would do.
Yes, yeah.
New York, San Francisco, Chicago, and then it's...
Yeah, I will go through this.
Yes.
Yeah, well, you can think that maybe diseases are really these things, no? This if you have P53, which is a knob, and you damage that, that's not very nice. So, if the damage is random, then these systems are quite robust to damage, and this is explained why the internet or why a biological network might have this topology. But actually, as it was said, if you have targeted attack, then the percolation threshold it pops up. Okay, and these systems are more prone to be dismantled in this case. So this is a kind of explanation of why do we observe so widely the degree distribution, this scale-free degree distribution, and why people are interested. It's not the only case. So if you have a Ising model, I don't know if this ring a bell to you, but the Ising model on this topology is always ordered, and until the discovery of these objects, it was only known that only one graph was known that did not display a phase transition, that was the chain. But the chain is always disordered, and these systems are always ordered instead. And you have many other critical phenomena. So there is a rich interplay between structure and dynamics that you put on the structure. Okay, so these scale-free graphs are important for dynamics. So let me just now present some of the tools that people have been developed to study model for this graph. And one of the most praised is this growing network model. And the idea is that most of the network grow, they increase new nodes and new links, and the attachment is not uniform, meaning that again, popular nodes are more likely to acquire new links. Okay? So, and I will show you that actually working with simplicial complexes can enrich our understanding actually of this kind of phenomena and how to think about this. But let me first tell you the traditional way of thinking and the way we teach the student in class. There is one of the most influential model, the BA model, which is based on previous result, the Simon model, the Sola Price model for citation network, but let's call it BA, which starts from a finite network, and then at every step we add a new node with M links or M edges. And these edges, let me just check. So one node and two links. And these two links choose the target node with the probability that is proportional to the degree of the node that is chosen. So the BBC will receive more links because it's a very important website. And just these two elements gives a scale-free distribution. Of course, you have to, the exponent is 3, is not changing, while in a real network you observe exponent that goes from 2 to 3. But actually, this is not a real problem. You can modify these dynamics to to generate a network with a different exponent in the interesting range. So the property of this model is that the average degree of each node increase in time, and actually like a square root of time, and actually the older nodes are the ones that get more links, and this is also called the fast mover advantage. There are also other models for which also latecomer can acquire many new links. But so this model is a very nice model from the theoretical point of view. It can be studied using the master equation approach, which is quite a very widely used techniques, but there is a little twist for the solution of this problem, because this is a growing network model. So the stationary state should be taken with a little bit more of care. So you write this master equation approach, which is a difference approach for the number of nodes that at time t have k links. So the number of nodes that at time t plus 1 have k links is equal to the number that at time t had k links, plus an addition, like a gain term, and minus a loss term. And the gain term is coming from the node that had degree k minus 1 at time t, but acquire a new link, so they enter into the class of node of degree k, and the loss term is the node that had degree k at time t, and they have degree k plus 1 at time t plus 1, so they leave this class. And you have to make a bit of be careful and distinguish between the nodes that arrive the class k equal to m, which acquires always a new node, and the other nodes. Okay? So this pi of k is the probability that the nodes of degree k acquires a link at time t for this model. So now usually when you have a master equation approach, what you look for the stationary state. So you should usually what you say is that the difference between, you would like to say that the difference between nk at time t plus 1 minus minus nk at time t goes to 0. But you cannot do that, because actually the number of nodes are increasing in time. So what you do is you assume that the degree distribution goes to a stationary state. So you assume that the number of nodes that at time t have degree k goes like the number of nodes, which is more or less t, and the degree distribution that is now in a stationary state. And then you solve this model, this master equation for the degree distribution. The time t simplifies, and you can find the exact degree distribution, which is a nice and neat decay with the exponent gamma equal to 3 for large k.
The number of nodes you added.
Sorry?
Little m was the number of nodes you added.
M is the number of links that you attach at each time. So one node with m links, so there is one node at each time that has one. So nice and easy. And the idea is that the traditional idea is that you need preferential attachment. If you get rid of preferential attachment, you will not be able to have a scale-free graph. And in fact, if you have a growth model with uniform attachment of the links to nodes, then you get an exponential degree distribution. So if you at every time you add a node with m links, but the nodes do not choose popular target node, but just random node, then you have an exponential network. And there is always the fact that older nodes are the ones that are mostly connected, but the average degree increase more slowly, and these abs are not significant, so that actually the system is much more homogeneous than in the case of preferential attachment.
It's a border, the DA model is borderline for being scale-free, because K equal 3 is just
Yes, it's borderline. There are many variations. So you can put an attractiveness, additive attractiveness, for example, that change the exponent. I also been working on it.
You still have Gaussian fluctuations, in fact, they're not
Logarithm
This is just widely the limit of
is in the limit.
But in fact, you fall into the Bayesian attraction of the Gaussian with the square root log n.
Well, I'm not sure about that, but I think this is really scale-free. So it's the second moment is diverging for, if you have a Ising model, it's always paramagnetic for this graph. I'm sure about that. It is always paramagnetic, yeah. So let me just put in this narrative the recent and less recent recognition about the importance of topology in network topology and geometry. So we have over the last 10 years we have devised a lot of measure for network structure, like characterizing real data sets. But actually, it is with the large availability of large data set, it's important to go further, and it is believed that actually developing a network topology and geometry is essential on this purpose. For instance, there are papers published like this in which the geometric structure of brain fibers have been the importance of the geometric structure of brain fiber has been stressed. And actually, this is also related to the fact that it might be, this is not conclusive, it's just a slide that I put there, to show that this is a scientific debate. It might be that actually the structure of the network going behind the universality property is important to understand dynamics. And in fact, in the brain, you would like to describe some spatiotemporal fluctuation of, for example, synchronization parameter. And if you have some modular structure, some hierarchical structure, there is some evidence that this is actually possible. So actually understanding the organization of the brain behind the degree distribution or the small world is fundamental in this purpose. And a lot of interest is also focusing on simplicial complexes, which are not formed just by node and links, but also triangles, tetrahedra, and so on. So I have some slides which are quite redundant in this context. Of course, we are interested of different simplices. The simplices have faces, and we know what is a simplicial complex here. So more interested is how you can use simplicial complexes to study network. And you can go from a network to a simplicial complex with a clique complex operation, which every clique is identified as a simplex. And on this view, one can revisit a method that had been proposed already more than 10 years ago for finding community in the graph. So what people now in this paper have proposed is that you have cliques, 4 cliques, and you roll the cliques. So this rolling means that you look for cliques that share 3 nodes with your starting clique. And you kind of rolling this clique, you find a percolating cluster. And in this way, you can find this clique percolation cluster in which some nodes can belong to different community. And this is a good method to determine communities in network, and in particular, overlapping community, when one node can belong to different community. And I want to show you a nice, very nice example that I have in this paper. This is a very nice data set of word association. So these are people that in an experiment have been given some words and had to write words that they thought were closely related. Okay? So it's a psychological test of how people conceive distance in the words. And so if you do this click percolation, you see that a word like bright belongs to different community and can be associated to yellow and then a cluster of colors, can be associated to light, to dark, or and this is another cluster, or to astronomy, or to intelligence. And this is how this algorithm is used, in which this is a very important problem in network to describe community, but community that might overlap, so that one node can belong to different community. And this is probably the first proposal, which use clicks, so like simplices, to do this percolation, generalized percolation problem. Another group instead is working on weighted networks in the brain, and they introduce a filtration using the weight of the link. So just by putting a threshold on the weight of the link, they introduce this filtration, and then they do homological study of this, and they find that actually this topological study are able to reveal difference that other methods are not able to reveal. Another approach is the direct approach, not just given the network you want to construct a simplicial complex, but realizing that many data actually have the form of a simplicial complex. And this has been the claim, for instance, of Giusti and others, in which they have this very nice paper in which they argue that in brain functional networks, there is a necessity to distinguish between 3 regions of the brain which are correlated pairwise and 3 regions of the brain that are activated at the same time. And one would be described by 3 links and the other by a simplex. You have also other data that are naturally in the form of simplices, like protein interaction networks, where protein actually do not bind pairwise usually, but they bind into complexes, but it's another complexes, and protein complexes, and so they form really simplices, okay? And or in social networks, you have collaboration networks, both in movie, co-starring in movie, or in science, when you co-author a paper in science. Not all the papers are single or 2-author papers, okay? In particular in biology or... Interesting, simplicial complexes have been used quite extensively already in the field of quantum gravity. And they have been used by people like Penrose, which was believing in some discrete fabric of the space, And here it has a beautiful citation of him in which he says, in my own view, is that ultimately physical law should find the most natural expression in terms of essentially of combinatorial principle, so it should emerge some form of discrete and combinatorial space-time. But other people instead believe that using network of simplicial complex is just a useful regularization of their continuous description, true description of space-time. And there are very different methods, like listed here in this paper. And here I just listed a bit. So causal dynamical triangulation is like really the idea of stacking simplices and polytopes. And you have tensor networks which use simplicial complex, and a causal set which use also network and so on. It's quite interesting how they use different discrete structure for their purpose. So here I want to tell you, I want to just to close a bit the loop, and yes, and tell you a bit about the research in my group, what we have been doing, and try to see how we can generalize growing networks to growing simplicial complexes. So we define a generalized, we consider pure simplicial complexes formed by d-dimensional simplices, and we consider the generalized degree, so the number of d-simplices incident to a phase. And we call them k d delta mu. D is the dimension of the simplicial complex, delta is the dimension of the phase, and mu is actually the phase. So for instance, here the link 1, 3 will have a generalized degree 3 because there are 3 triangles incident to it. The node 3 has generalized degree 4 because there are 4 triangles incident to it. So then we define a auxiliary quantity for d minus 1 phase, which is the generalized degree minus 1. So just in this case, just for links, we use the generalized degree minus 1. And one can see that actually the constraint to have manifold here is that this incident number should be at most 2. So for example, in d equal to 2, you should have every link at most connected to 2 triangles. Or in d equal to 3, you should have 1 triangles at least incident to 2 tetrahedra. And we can actually formulate a growing simplicial complex model that we call network geometry with flavor, in which we start with a D simplex, and at each time we add a new D simplex with a new node, and this D simplex is attached to one existing D minus 1 phase. So for example, we attach, at the last time here, we attached these triangles with a new node and we glue it to an existing links, that is link 5, 3. And this attachment rule, the way in which we choose a link, is chosen according to some rule that include a parameter that we call flavor that takes the value -1, 0, and 1. And so this rule reads like this. So it's proportional, the probability of attaching a 2 simplex to a phase mu is proportional to 1 plus S n mu, where n mu is this incidence number of the phase. So let's look a bit closely at this probability. So if S is equal -1, actually we can attach a new D-simplex only to a D-1 phase that has an incident number 0. So we can just have 0 and 1, and an incident number 0 and 1, and so we will construct manifold. If S is equal to 0, we have a uniform attachment to every D-1 phase. And for S equal to 1, we have a generalized preferential attachment in which we choose a D-1 phase proportional with a generalized degree. So what do we get? In D+1, nothing surprising. This is exactly the story I was telling you. We need preferential attachment to have scale free. For uniform attachment, we have exponential. And for the manifold, we just have a chain. What happens instead for D equal to 2? Well, for D equal to 2, also the uniform attachment generates a scale-free graph, because actually I'm attaching a triangle to any random link. So I will end up attaching a new link to a node proportionally to how many connections it has already. So this is an emergent preferential attachment. And the manifold is an exponential network. What happens in D equal to 3? Well, also the manifold becomes scale-free. And the reason is that if you think of how these tetrahedra are stacked one to other, and you look, for instance, at node I here is attached to 3 tetrahedra. It has generalized degree 3, and there are 5 phases to which we can attach new tetrahedra. If we attach a tetrahedra to node I, then the node I has generalized degree 4, but now the number of phases increase to 6. And this generates a kind of emergent preferential attachment just due to the geometry. So we can do the master equation approach for this generalized degree distribution. The probability that a delta phase increases generalized degree at time t can be calculated with some simple combinatorics, long but simple combinatorics argument. And actually, the generalized degree has a very regular pattern. So not only these networks have this degree distribution that is scale-free, as I mentioned to you, but also the generalized degree distribution follows a very regular pattern, so that for S equal to 1, we have always preferential attachment. All the delta phase are all power law, and for S equal to 0, the D-1 phase is exponential and the other power law, and for S equal -1, one is bimodal, one is exponential, and one is power law. So depending on the dimensionality. So the generalized degree distribution of the triangle is bimodal, because you can only put 1 tetrahedra or 2 tetrahedra. The generalized degree of the link is exponential, and the generalized degree of the node is power law. And the generalized degree of the node in 3 dimensions is associated with the degree, is simply associated with the degree of the node. So in this, you can get the degree distribution, and it fits perfectly well with simulation. So now, how can we see more geometrically this object? Well, if we want to constrain the link of having all the same distance, we can put them on a circle and a Poincaré space, really, because topologically is a circle, but if we impose that the distance of the links should be the same, although infinite, you can put it in the Poincaré disk. And similarly, the topology in D equal to 3 is a sphere, but you can you can, if you impose that the distance are all the same, this sphere should be interpreted as a H3 space. So let's look at the position now of the nodes on the surface of the sphere.
Can you explain once again how the hyperbolic structure appears?
Well, you can just impose that the distance is the same for every link, and we don't have a real proof of this, but maybe it's a conjecture or numerical thing, but we believe that the only configuration in which we can have a simplicial complex in which all the distance of this topology and all the distance of the links are the same, and is a hyperbolic. But you pay this with the distance that are actually infinity. So if you just forget about this hyperbolicity now and just put the position of the nodes on the sphere and project on the plane, and where these are the azimuth and the angle, you find this pattern that actually maybe you recognize. This is what we call Apollonian networks, but you call triangulation or things like this. So this comes from having a triangle, and these Apollonian networks we construct like this from Apollonian packing, where these Apollonian packing are constructed by tangent circles or sphere, and we put a node at the center of the circle, and we put a link if the two circles are tangent to each other. So how to see that this stacking of polytopes generates this? So for example, look at these triangles orange, red, and yellow, which are here orange, red, and yellow. Oops. Oops. Sorry. And you have that the new orange point is the one in triangulating this triangle here. So you project this on plane, and this red is triangulating this, and this is triangulating that. So this is the construction from the three-dimensional stacking to the two-dimensional Apollonian network. Okay, so I think this is a good place to stop. And we have shown that actually there has been a lot of discussion about the role of preferential attachment to generate scale-free graph. And these claims are backed up by results on real data, on some real data, but there are also other methods to generate scale-free graphs, starting only from topological construction. So instead of using nodes and links, if you start to use simplicial complexes, preferential scale-free degree distribution can emerge just from the topology of these networks and the different dimension of this graph. Thank you very much for your attention.